In this video, I'm going to tell you the story of how I built a 2D simulator for robotics from scratch. This video is part of a larger video series where I program a sumo robot as a way to demonstrate embedded systems programming. And I've now come to the point in this video series where I've implemented all the drivers, and it's time to implement the application code to give this sumo robot its autonomous behavior, which is to locate and push its enemy out of the platform. But to implement this application code directly onto the robot is time consuming, because after all it's an embedded system, so I must flash the microcontroller for each code change I want to test. So for a smoother development experience, I'm instead going to simulate my sumo robot, which also gives me an ample opportunity to showcase my simulator project in this video. The idea here is that since I've separated my code into hardware-dependent code, the drivers, and hardware-independent code, the application code, I should be able to write and test the application code with the simulator on my host computer, and then transfer this code directly onto my actual target, the sumo robot. 2 sumo robots on a circular platform is a fairly simple scenario, so there is no problem simulating it. But when I originally got the idea and went searching for a suitable simulator, I was annoyed by the available simulators out there. Most felt overkill for what I needed. Many have clunky user interfaces, are messy to set up, has complicated graphics, and so on. Because for what I wanted to simulate, all I really needed was a simple 2D simulator. And this finally led me to, for better or worse, to implement my own simulator. The first thing I did was to set some project goals. First of all, I wanted it to be a simple project, function over beauty. So 2D and no 3D graphics. 3D is cool, but adds unnecessary code complexity for many simulation scenarios. Moreover, my graphics should be simple and there should be no sophisticated user interface. It should be a simulator aimed at programmers. My goal was for the codebase to be simple and flexible so that the simulation could be configured through code rather than a graphical user interface. And this further meant a minimum number of dependencies and a well-structured codebase. And I also wanted the target code to be clearly isolated from the rest of simulator code so that it would be easy to transfer it from the simulation to the actual target. I decided to write it in C++, mostly because I was writing a lot of C++ code at the time, but also because C++ is a suitable language for an object-oriented project like this. Finally, I wanted it to run on both Linux and Windows. I prefer Linux, but I realized many are stuck with Windows, and that was it for the goals. Now to the details. There are many parts that make up a simulator. And at first it was hard to get a grip on where to start, because there are not a lot of resources that explains how to build a simulator yourself. But when I thought about it some more, I realized that a simulator is very similar to a game engine, and there is no lack of resources on game development, and this was something I could leverage while developing this simulator. But broadly, the parts that make up a simulator are, first of all, the physics engine. As you know, the real world is governed by laws of physics, and a simulator meant to simulate real objects needs some code to resemble that. Secondly, it's good if the simulator has graphics. While it's not functionally necessary, it makes it much easier to see how the simulation is going. Thirdly, it needs some sort of input and output system. The objects acting inside the simulation needs to get their input from somewhere. This can, for example, come from a keyboard and a mouse, or from code, which is going to be the case when I simulate with the application code of my sumo bot. And finally, it needs a software architecture to glue everything together. I mean, the simulation scene and objects must be represented in some way, and there needs to be some sort of main loop to ensure everything gets executed in the right order. I'm now briefly going to explain how I implemented these parts in my simulator, but I will keep my explanation pretty brief, so if you want more details, I will leave a link to a more detailed blog post in the description, and all code is also, of course, available on GitHub. Note one last thing before I get going. What I'm showing here is not meant to serve as a guide on how to implement a simulator. I'm just explaining how I did it, which may not be the best or even a good way to do it. Anyway, getting started. The physics engine is probably the best place to get started, and it's also where I began my implementation. The big decision here is whether to implement your own or to go with an existing one. I figured it was dumb enough to implement my own simulator, so this time I decided to go with something existing. There are many existing physics engines, but I picked one called Box2D, which is an open source 2D physics engine used by many popular 2D games. But while picking an existing physics engine saved me countless of hours of implementation time, it wasn't without its problems. The first problem was that I needed to simulate 2D from a top-down perspective, but Box2D as well as other 2D engines are aimed at simulating side view perspective. But I was able to get around this by disabling gravity and using the friction features of Box2D. Kind of a semantical hack, and it's not perfect, but after some tuning it turned out good enough for my use case. On another side note, it's important to remember that while you can spend a lot of time making a simulator realistic, it adds complexity, and many times a rough approximation can often be good enough. The simulation doesn't have to match reality exactly to be useful. And this was something I had to keep on reminding myself of during my implementation. Then after having an acceptable 2D view, the next thing I implemented was a simple DC motor model, because that's what my sumo robot has. And similar to a real DC motor, this model takes voltage as input and produces a force as output. It's a very ideal model, but once again, good enough of an approximation for my simulation. Then I continued by modeling my sensors. Here I had to consider the features available in Box2D. I implemented the range sensors by using the raycast feature, which essentially casts a ray between two objects and then gives the distance between them. The line sensor was less straightforward, but I figured I could represent the line as an invisible body and the sensor as a tiny body, and use something called a contact listener for collision detection to detect when they collide. After all that hacking of Box2D's semantics, I had the physics in place, so then it was time to move on to the graphics. Because up till this point, I had just been using the graphical user interface in the testbed provided by Box2D. When it came to the graphics, I had little prior experience with graphics programming, and I quickly realized it was a jungle. There are so many APIs, libraries, frameworks, and engines available. Before jumping on board with anything, I once again took a step back and considered my goals again. First of all, as I said before, I wanted something simple. Function over beauty. Only simple shapes and graphics. And I wanted a simple codebase written in C++ with few dependencies, and I wanted to support Linux and Windows. And for these reasons I decided to go pretty bare and implement my own renderer on top of OpenGL, but with some OpenGL helper libraries to avoid going completely insane. More specifically, GLFV and GLAD. This gave me much flexibility and few dependencies, but of course meant I had to learn a lot more about graphics programming. I'm not going into all the details here, but to say the least, there is a lot that goes into even drawing a simple triangle with OpenGL. First, you need a buffer that describes what the GPU should render. Then you need to describe what this data is and how it's laid out. Then you need to tell the GPU what to do by giving it a special program called a shader. And with the selected buffer and shader, you can then finally execute a draw call. After figuring out how to render a single triangle, I went on to draw other shapes, which led me to the fundamental idea that everything you render is made up of triangles, because triangles have properties that make them mathematically faster to draw, and they are what modern GPUs are optimized for. A rectangle was trivial. It's just two triangles, a circle less so, but with enough triangles you can render what appears to be a circle as well. And with enough triangles you can also represent any other shape. Besides the basic shapes, I of course also wanted to be able to render them at different position with different rotation and scale. And to avoid creating a separate buffer for each case, I only describe the shapes at their default and use linear algebra to transform them. And for this I dragged in another dependency, a math library called GLM. Next, I implemented zooming and panning. Zooming is the same as scaling up and down the rendered objects, and panning the same as moving the objects in the opposite direction, both of which could be easily implemented with another transform matrix. Then I also wanted a basic user interface, a simple menu to toggle between scenes, to tune parameters, and to show statistics. Doing this from scratch with OpenGL is kind of a mess, but luckily there is a great library for this called IMGUI, which lets you add advanced menus with just a few lines of code. Finally, to top it off, I added texture rendering, completely unnecessary and kind of violates my goal of function over beauty, but it wasn't too much work and gave my simulator a cooler look. For this I dragged in another library called SDB image for loading the texture and wrote another shader program to interpret the texture data. I now had a renderer in place, far from optimized, but it was good enough for what I needed. And with physics and graphics in place, each on their own side, it was time to bring the two together. And this was when I really had to think about the overall software architecture. What brings physics and graphics together is essentially the objects they describe. For example, my sumo robot is composed of motors, sensors and a body, all of which has their own graphical and physics properties. There are different ways to solve this design problem. Some solutions lean more towards inheritance, while others more towards composition. Inheritance is perhaps more intuitive, but can break down when things get more complicated, while composition can be harder to implement but provides looser coupling, which makes the code easier to extend. My simulator project is comparably simple, so it doesn't matter too much, but I still decided to go for an implementation leaning more towards composition. I didn't go as far as implementing my own entity component system, which is a common compositional pattern in game development, but instead went for a simpler, object-oriented yet compositional approach. My design unsurprisingly consists of objects, which I call scene objects. These describe the entities in the simulation and are made up of different components. And each scene object can have at most one of each of the following component types. The renderable component describes the graphics of the object, basically what shape it is and what color or texture it has. The physics component describes the physics behavior of the object. And the transform component describes the position, dimension and orientation. But it also acts as the link between the physics and graphics component by letting the physics component write to its data and the renderable component to read its data. Finally, I have the controller component, which holds the input and output logic, whether it comes from a keyboard, mouse or a piece of code. Just to give you an example, to simulate a falling box, I create a scene object composed of a rectangle component, which is a renderable, a rectangle transform and a physics body. And then in each simulation iteration, the physics body updates the position and orientation of the transform, and the renderable component then reads this data and draws the rectangle on the screen. And this falling box, since it's not controlled by anything, it has no controller component. After all this work, it was a satisfying moment when I saw my render come alive with my physics for the first time. Moreover, to create a more complicated scene object, like a sumo robot, I made it possible to compose scene objects of other scene objects, which also has the added benefit of better code reuse across different scene objects, because, for example, the wheel motor object is not only useful for a sumo bot, but also for other types of robots. Further on, the scene objects of course don't live on their own. They need to be attached to a scene, and I represent a scene as another class, and this class holds the simulation session, including the physical world and the list of scene objects. Regarding the implementation of all of these components, the renderable component, the physics component and the transform component were all fairly straightforward to implement. What wasn't as straightforward was the controller component. While getting the input from the keyboard and mouse was easy because GLFE provided callbacks for that, what wasn't as obvious to me was how I was going to connect the controller component with the physics component, because the interface for the different physics components were different. I mean, the DC motor model takes an input, voltage, while the distance sensor gives an output, distance in millimeters, and the line sensor gives an output bool, and so on. And catering for all of these different cases in the controller component would not only make for an ugly interface, but would also make the controller code harder to separate from the rest of the simulation code, which was important because I wanted that code to be easy to transfer to the actual target. And this meant I had to come up with a better solution, and what I came up with was a concept called voltage line, which is nothing but a pointer to a float, where the float value represents a voltage level. I make each physics object provide one or several of these voltage lines. For example, the DC motor is straightforward since it already takes voltage as input. But for the sensors, I have to convert their outputs to a corresponding voltage level. Then I can represent the microcontroller as a controller component, which takes a list of assignable voltage lines. Not only does this make it easy to connect the controller component to the physics components, it also makes intuitively sense, because on a real robot, the microcontroller are connected with sensor and motors through wires with voltage applied to them. There's more to this side of the code, but I will get into that in the next video. Finally, the way the execution comes together all the way from input to physics to graphics is through a main loop, which is the same as the game loop in game development context, which is nothing but a while loop that executes each step of the simulation at a set frequency. More specifically, in my simulator, I created a base class called application, and this class handles the initialization of everything and holds the simulation scenes and menus. And this class must be inherited by the user of bots2d, and I coded it like this for flexibility, because it lets you as a user decide what scenes and menus you want to include in your simulation application. And what this means is that my simulator, bots2d, is technically not a simulator, but it's actually kind of a framework for creating your own simulator. This means that in your simulator application, you will have a main function that instantiates your application class derived from application, and then you call the run function on this, which in turn starts the main loop. And then in each iteration of the main loop, it first updates the physics, then the controllers, and finally the scene is rendered. And that's the story of how I built a 2D simulator for robotics from scratch. This project was a good exercise in programming that taught me a lot of C++, object-oriented programming, and other things. But in hindsight, I kind of regret embarking on this journey. It just took too much time. After all, my interest lies with embedded systems and not game development. It would have been more pragmatic of me to just pick an existing simulator, even if they are not perfect for my scenario, or to quickly throw something together in Python, or to directly develop on my sumo robot. But oh well, now the damage is done, and once again you can find it on GitHub, and I've left a link to a detailed blog post in the description. In my next video, I will use this simulator or simulator framework, bots2d, to implement the application code for my sumo robot. But until then, thanks for watching and see you next time.